external unbalanced force. Would be an atom, for example. And remote non-simultaneity is something that I will discuss. It's an important part of special theory of relativity. In the picture, I also show Galileo Galilei. He is the author of the relativity principle, which will be mentioned many, many times in my talk. And the other side, you see one of the instruments that he used in his work. So that's a short introduction. Let me get right down to the point. A key prediction of Einstein's theory, I hope you can read these things on the screen.
Yeah.
I'm an American, so I speak American English. I'll try to be slow if, you know, that's sometimes the problem with somebody who's speaking his own language. This remote non-simultaneity is derived, as it says, from the Lorentz transformation, and shows the equation. I'll give the meaning of the variables here. Note this gamma is very important on the right-hand side. Einstein famously used this example of two lightning strikes on a moving train. The distance separating the strikes to the vantage point is this delta x that you see. The speed of the train relative to the platform is v. And the time separating the strikes, the two lightning strikes hitting the train, that time is delta t. Those are the definitions of the variables, straight from the Lorentz transformation. So the corresponding time difference, expect a different time difference on the train clock, we refer to that as delta t prime on the left side. So what you can see is that delta t prime on the left side can be equal to non-zero even if delta t is equal to 0. In other words, because v and delta x are non-zero, if delta t is 0, then delta t prime will not be 0. So delta t 0 means simultaneous, and delta t prime means, if it's not equal to 0, it's non-simultaneous. So the fact that if you have v and delta x not equal to 0 and delta t equal to 0 simultaneous, that delta t prime can be different than 0, that is non-simultaneous. This has been taken for 100 years or more to mean that this remote non-simultaneity, this effect, which that is that events which are simultaneous for one observer may not be so for another. It's been, because of this fact, this has been assumed to prove R and S. It's clearly based on the Lorentz transformation. Okay, so this is the real crux of the point here. Einstein overlooked something crucial in his derivation. The clocks that are used to measure the two time differences on the train and on the platform are freely translating through space. That's the assumption. There's no force acting on them. As a consequence, we just said, the rates of these clocks are perfectly constant. Each one of them is constant. They cannot change spontaneously. This is because of the law of causality. That's a way to say it. This goes back further than Einstein and Newton, just probably back to the Greeks at least, that in order for something to happen in physical circumstance, there has to be a cause. There has to be something making this change. And that distinguishes science basically from religion, because in science we only deal with measurable quantities, whereas in religion many of the most important things are not measurable. For example, angels. So we're in the business of science, so we believe that things only happen for a cause. An example where the law of inertia is used is the first law of motion of Newton, called the law of inertia sometimes. The idea there is that if an object is moving freely, no such forces, it will continue on in the same speed and distance, same speed and yeah, and so as you say, velocity, same direction, indefinitely. There has to be some outside force affecting the object before it's going to change its velocity, either direction or speed. That is goes along with the law of causality, that there has to be a reason for physical changes. Now, in the present case, if we go back and think about these clocks, which according to the law of causality have constant rates, the obvious thing is that if you take the ratio of these two rates, that this ratio must also be constant. And I'm calling that ratio Q to give it a name. So you have two constants, you take the ratio of those, they're also going to be constant. That's, I think, something that's self-understandable. As a result, the time differences for the same two events, in other words, if you use these two clocks, which have this constant ratio, the time differences they mentioned for any two events will be in the same ratio. So I like to use the example of that I had when I was first coming to Germany from the United States, is I brought along an electric clock, and the clock, I plugged the clock in Germany to keep track of the time. And when I woke up, I found out that although I thought it was going to be 11 o'clock, it was actually 9 o'clock, because the rate of the clock in Germany is 50 cycles per second, and it's considered to be 60 cycles in the States. So in other words, the rate of these two, the rate changed between the United States and Germany, and that of course affected the fact I woke up too late. It's as simple as that. So, but if you look at the equation more carefully, you see that if one of the time differences is zero, that is, if you have delta t prime is delta t over q, if one of them is zero, the other has to be zero as well. So that again goes back to this constant rate business, law of causality. And that means absolute simultaneity, which is the opposite of RNS, of non-simultaneity. So you get, in other words, you get simultaneity if you assume that the rates of these clocks are constant because they're inertial. And if you assume the Lorentz transformation, you get the opposite. So the way that I like to look at this is that there's a discussion here between the law of causality or not. So you have a choice. You can say, I don't believe in the law of causality, or you can say, I do believe. Now, if you don't believe it, you're in shaky grounds because you're dealing with the history of science over at least a couple of centuries. People always assume that there must be a constant, that there must be a cause of something. I'll give you an example. If you have water being formed from oxygen and hydrogen, if you just look at the situation, you have some oxygen gas and some hydrogen gas, you put them together and boom, you get heat and water. And the supposition is that there must have been some cause that made this change. And of course, what we know is it's chemistry. You know that bonds are broken because of the contact of the oxygen, the hydrogen, and so on. But it's just an example that you believe that there's a reason for oxygen and hydrogen to come together. It's not just something that happens by itself. So there are two questions then. If you take the position that I'm asking you to think seriously about, that the rates are constant and therefore that the law of causality holds, then you have to look at the theory from a different point of view than if you look at it from the Lorentz transformation. So in a way, it doesn't prove the Lorentz transformation is false, but it says that you have to believe, you have to not believe in the law of causality in order to believe in the Lorentz transformation and in remote non-simultaneity. So a sensible way to proceed then is, without arguing any more about the law of causality, is if you're going to go ahead and say that the Lorentz transformation is invalid, and I'm asking you to think this, there's two obvious questions that have to be answered. One of them is, how do you explain the fact that over 100 years, there have been many successes of the Lorentz transformation? It's undoubtedly true. I mean, people have thought about this as being a very valid method of science and so on. So how do you explain the success it had if it's not a valid transformation? And the second thing is, and this was pointed out to be my barber, by the way, I succeeded in getting him to think that these clocks should have constant rates, and that this was the proof that the Lorentz transformation is valid. And he said, well, Bob, okay, that's great, but I mean, you can't just throw something away. You need something to replace it. So that's the second question, is what can be done to improve relativity theory once you say, okay, let's try a different approach where the Lorentz transformation is no longer used. Okay, so the answer to the first question is that the successes that you find from the Lorentz transformation invariably come from application of what's known as the relativistic velocity transformation. I'll show you that in a second. It has to do with the velocity transformation. And the Lorentz transformation is connected with the relativistic velocity transformation. But there's another transformation that is also compatible with the RVT. So the point is, just because the RVT works doesn't prove that the Lorentz transformation works, because there's also another transformation that is compatible with the RVT. So that's really the answer to the first question. The successes are based not directly on the LT, but on this velocity transformation, which looks to be very valid transformation. Okay, the second answer can be summed up in a single word, as I say, objectivity. And what this means is that there's only one reason that two observers can reasonably disagree on the value of some physical quantity, and that's because they use different units to express their results. So, examples. The train is again useful. If the clock on the train runs slower than the one on the platform, then according to the definition I gave you, Q, this constant, is greater than 1 for the platform observer. So that means that when he gets a time from the train, in order to get it on his time scale, he has to multiply with this constant Q. On the other hand, the corresponding constant for the train observer, in other words, the reverse direction, is 1 over Q. 1 over Q is then less than 1. So this reciprocal relationship is quite normal in everyday life. For example, if you want to change $1 to cents, you take 1, the number 1 for a dollar, and you multiply it by 100, and that tells you there are 100 cents. But if you want to go in the other direction, you have to know that 1 cent is only worth the reciprocal of that, 1/100th of a dollar. So if you have 1 cent, that's only $0.01. So there's this, excuse me, there's this reciprocal relationship between, say, conversion factors in the two directions. In one direction, you use 100 to go from dollars to cents, and the other one you use 1 over 100. STR is subjective. It claims that the platform observer thinks that the train clock is running slower by a factor of gamma V. I've introduced that before. Whereas the train observer thinks the clock on the platform runs slower than by a factor of gamma V. This is the necessary result of the LT. That is, it's symmetric, it's subjective. It's a matter of whose clock you're using to know which one is slower. So this is a necessary result of the Lorentz transformation. I won't show that here, but everyone would agree that you get this symmetric time dilation, you call it, the symmetry between the clock values from the Lorentz transformation. And so, but if you say the LT is invalid, then you can simply ignore that and go back to thinking, okay, I like a theory which is objective. I like a theory which, so we actually agree on how much time elapsed, but we have to check our clock rates, and we have to realize that if the clocks aren't running at the same rate, we need a conversion factor in order to come up with the same number. In absolute terms, the elapsed time is the same for everybody, but the value that you read from your clock will be different in the two cases, but it can be corrected very simply if you know this cue. So, I went back one too far here. The question is, therefore, can we fix the problem without destroying the theory as a whole? This is the barber's question. Can you include this ratio delta t prime over delta t as a constant for a pair of inertial frames? Here you have it in red. Lost my arrow. But is the clock rate proportionality compatible with Einstein's two postulates? Okay, so the answer to that is, to go back to this relativistic velocity transformation, which I mentioned before, to answer the first question. Here it is, ux, uy, and uz are speeds in the x, y, and z direction, so that by definition, it's delta x prime divided by delta t prime, space divided by time. And you have three such equations for the three spatial directions. And according to the relativistic velocity translation, which was derived in Einstein's 1905 paper, it was possible to derive it in earlier work. For example, one in 1887 from Voigt also allows you to derive the velocity transformation from his transformation, which is not the same. Okay, important in this definition is eta. You see, eta appears in all three equations of the velocity transformation. This is not something new that I've cooked up. You can see it in any relativistic book, what the relativistic transformation is, and that this eta is defined in this way. It depends on the speed, the relative speed. It also depends on delta x, which is, again, the difference between the two rest vanes. C is the speed of light, delta t is the time difference. So in order to use this delta t prime and delta tq in a valid transformation, you start out with something which is valid, namely the relativistic velocity transformation, and you simply multiply each of the three equations with this one. Delta t prime equals delta t over q. So let's look at uz prime, for example. It's the velocity delta z prime over delta t prime. If you multiply on the left by delta t prime, you get delta z prime. On the right, if you multiply by delta t over q, you get z and eta over gamma q. Right? You introduce a factor of q on the right side. You change uz into delta z. And so that gives you a new transformation. Now, this is different than the Lorentz transformation because there it's much simpler. Delta z prime is equal to delta z, and delta y prime is equal to delta y, and delta x is, this eta is replaced with a gamma, and the q is missing entirely. So this new transformation that I'm showing you here, different than the Lorentz transformation. It's obviously compatible with the velocity transformation, which is important because it's correct. And to give this a name, I've called it the Newton-Voigt transformation. Voigt, as I mentioned, came up with the first space-time transformation that recognized that you can change the equations of the standard Galilean transformation in such a way that you have the light speed constant. And I put Newton's name in there because he is always was very emphatic about simultaneity. So anyway, that's what I'm going to call it from now on, Newton-Voigt transformation. Okay, the NVT also satisfies Galileo's relativity principle. To save time here, I'm not going to show how that goes, but that's a very important point, is that Einstein colleagues thought that only the LT can satisfy the relativity. And this is a key misjudgment. The the NVT also satisfies. Now, this is a more practical problem. Is the NVT, if you recall, requires an explicit value of the parameter Q to be applied for any pair of rest vanes. So that's different than the LT. You don't need any special parameters. Gamma just depends on the speed of the two rest vanes relative. So that's, if you will, a problem, or at least it's an essential point, that in order to use the NVT, you got to know what this Q is. So how do you do that? You do it by experiment. And how to do this was shown by two key experiments. One in 1960 with a high-speed rotor was carried out by Hay et al. And the other is with atomic clocks that have just been developed in around 1970, which were carried on circumnavigating airplanes. They went around the world with in both directions using these atomic clocks. What both of the experiments show is that the rates of these clocks decrease as the clocks increase their speed relative to a definite rest frame. And I call that the objective rest frame. So in the case of the rotor, it's the laboratory or the axis itself. So the question is, how fast is the clock going relative to the laboratory? In the case of the Hafele-Keating airplane experiments, it turns out that the ORS is the center of the Earth, the center of mass. They said it quite a little bit differently. They said it's something to do with where the axes of the universe meet. But I mean, it all comes down to the center of mass of the universe. Okay, so the Q can be determined if you know this objective rest frame in a given case. Normally, it's just when you have acceleration, it's the point of acceleration. So you can calculate Q knowing the velocity of the object relative to its origin. This experimental result is known as the universal time dilation law. That's the name that I gave it. You see, it's very simple. It's an inverse or direct, what do you call it? Proportionality relationship between times and speeds of the clock. So what it says in word, the measured elapsed time of one inertial clock, which is moving with speed v relative to the ORS, this specific rest frame, is inversely proportional to gamma v. So that's what it says here in the case of one clock where speed is v, and in the other case, you get a different delta t prime, a different time difference, and that depends on v prime. So if you combine the UTDL here, this equation, with the simultaneity equation, delta t prime equals delta t over q, you just have a plug in here, delta t prime is delta t over q, you cancel the delta t's, and you end up with q is equal to this. So if you have this information about the speeds of the two objects, this objects, you can calculate the value of q. And it's also good to know that if you want the inverse of this equation, then I mentioned Galilean inversion. That means that you change the signs of the speed and you interchange the meaning of the variables. So when you do that, you should get the inverse of the equation, and that leads you naturally to this. Q becomes q prime, which is 1 over q. That is to say, gamma v over gamma v prime is the inverse of a reciprocal of gamma v prime over gamma v. So this is an agreement with the objectivity principle of the NVT in contrast to subjectivity. In other words, one guy thinks that your clock is slower. On the other hand, you think that his clock is faster. Reciprocal relationship, not symmetric relationship. Okay, the UTDL is a very practical thing. If there's one thing in life that you can say was due to relativity theory, that's very helpful, is the global positioning system, GPS. And the way the UTDL comes into this is that the engineers knew that the rates of the atomic clocks that they're using vary with the speed of the satellite relative to the Earth. And they have to then take account of the change in the rate of the clock on the satellite so that it runs at the same rate as the one on the ground. And the UTL is used for this purpose. There's also a gravitational effect, I'll talk about that briefly, that is used to account it. But that's what they do. They change the rate of a clock before it goes up into the, with the satellite after it's been launched. And so that when it gets there, its rate is exactly the same or almost exactly the same as the rate of the clock on the ground. They need that. If they know then the difference of times based on the clocks that are running at the same rate, they just have to multiply that by the speed of light. So when a signal is sent from the satellite to the ground, they know it's going to go with the speed of light. Okay, that's something in relativity too. And in that way, they can judge then what the distance is. The rest is very complicated. You have many satellites. You have to solve some algebraic equations in order to put everything on one level. But the basis of it is that you have to realize that the clocks on the satellite do not run at the same rate on the ground. So people often say, oh, this is great. This is a great success of SDR, but it's only partially true. Arranging that the ground and satellite clocks run at the same rate only makes sense
Excuse me.
if events occur simultaneously, both rest fade.
Excuse me, Professor Goenka. Excuse me.
Yes.
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 Yes. We need to stop now for a minute, and we'll use the
All
next
right.
word and next ID to log in again. So I request all the participants also to use the next password and next meeting ID and kindly log in immediately. Okay. We can start from this slide. Thank you.
Right.
Yes.
Okay. So I have to go to the point where I can put in my ID and all that.
Yes. Now I'll close it and we can all